Vibration analysis, shaft alignment, techniques and practices for precise machinery alignment. Shaft alignment fundamentals. This introductory slide presents the overarching theme of shaft alignment. Shaft alignment is a foundational practice in rotating machinery maintenance, ensuring that two coupled machines, such as a motor and pump, share a common rotational centerline. Proper alignment minimizes wear, reduces vibration, and extends equipment lifespan. Misalignment issues can lead to premature seal failure, bearing wear, and increased power consumption. This presentation provides a structured review of shaft alignment principles, diagnostic practices, measurement methods, tolerances, and correction techniques. The goal is to provide reliability engineers, vibration analysts, and maintenance technicians with a comprehensive technical foundation to perform and assess shaft alignment effectively. The slide sets the stage for a professional engineering briefing that includes diagrams, procedures, tolerances, and alignment verification methods. Agenda: Introduction to shaft alignment, pre-alignment tasks overview. This slide outlines the sequence of topics addressed within the presentation. It provides participants with a structured expectation of the information flow. Topics include an introduction to shaft alignment concepts, pre-alignment tasks, measurement techniques, tolerance criteria, methods such as straightedge, feeler gauge, dial indicators, reverse dial, and laser alignment, dynamic movement considerations, and correction processes such as shimming and lateral adjustments. The agenda helps align participants with the progression from foundational principles to advanced methods and practical field techniques. Shaft alignment refers to the precise adjustment of machine components so their rotational axes coincide. This slide explains how improper alignment contributes to radial and axial loading of bearings, excessive vibration levels, and reduced equipment reliability. Shaft alignment is necessary whenever machines are installed, after foundation changes, following maintenance activities involving dismantling, or when vibration data indicates potential misalignment. The content emphasizes the difference between intended machine geometry and actual operational conditions influenced by thermal growth, pipe strain, and structural distortion. It highlights alignment as a precision task requiring trained personnel and calibrated tools. Pre-alignment tasks ensure that the machine and work area are prepared before readings are taken. This includes cleaning the machine base, removing rust and debris, verifying that coupling components are in acceptable condition, ensuring the machine is safe to work on, and checking that all guards and hazards have been addressed. Pre-alignment tasks also involve ensuring the correct personnel, tools, alignment instruments, and shim materials are available. Proper preparation significantly reduces setup errors and diagnostic confusion during alignment. Collecting as-found readings, creating a clean work area, preparing shims. As-found readings document the machine's condition before any corrections are performed. This slide explains the importance of capturing initial dial indicator readings or laser alignment system measurements to understand the magnitude and direction of misalignment. As-found values help verify whether misalignment is the cause of observed vibration issues. Documentation also assists in quality assurance, enabling comparison against post-alignment values to confirm improvement. Working around rotating machinery requires a clean, stable, and well-lit area. Dirt, debris, and oil residues can affect shim placement, bolt tension accuracy, and safety. A clean environment reduces measurement error by ensuring that surfaces contacting shims, dial indicator bases, and laser brackets are free of contaminants. The slide emphasizes proper housekeeping as a foundational engineering practice. Shim preparation is essential for vertical alignment correction. Shims must be clean, flat, corrosion-free, and in standard thickness increments to avoid soft foot conditions. This slide discusses selecting stainless steel pre-cut shims, verifying thickness using micrometers if necessary, and ensuring shims are inserted without burrs or distortion. Incorrect shimming can introduce angular errors, affecting both horizontal and vertical alignment. Care of bolts, preparing machine foundations, checking machine physical condition. Bolts secure machine feet to their foundation. This slide explains that damaged or dirty bolt threads affect torque consistency and cause sliding during lateral corrections. Proper lubrication, cleaning, and inspection are necessary. Under or over-torqued bolts may cause misalignment drift after readings are taken, invalidating measurements. Reliability-focused alignment practices require torque-controlled tightening methods. A machine's foundation affects alignment integrity. This slide describes checking for cracked grout, deteriorated concrete, loose anchor bolts, or hollow areas beneath baseplates. Foundation defects cause machine movement during operation, leading to variable misalignment. Proper foundation assessment ensures corrections are stable and long-lasting. Physical inspection validates that the machine is structurally capable of holding alignment. Technicians must inspect couplings, bearings, housings, shaft journals, and machine feet. Deformations, looseness, or wear can distort alignment readings. The slide reinforces that alignment adjustments cannot compensate for underlying mechanical faults. Alignment tolerance, tolerances and speed, published tolerances. This slide defines alignment tolerances, including angular and offset tolerances. Tolerances specify acceptable deviations between coupled shafts. Excessive deviation increases vibration levels and mechanical stress. Tolerances depend on machine size, running speed, and coupling type. Standards emphasize achieving precision within industry-accepted limits for high-speed machinery. Rotational speed directly influences acceptable misalignment levels. High-speed machines require significantly tighter tolerances due to increased centrifugal forces and dynamic loading. This slide explains why machines above 3,600 revolutions per minute often require laser alignment grade tolerances, whereas slower rotating equipment may tolerate greater offset or angular deviation. This slide highlights commonly referenced published tolerances from standards and equipment manufacturers. It explains that while general tolerances exist, many OEMs specify stricter limits for high-performance systems. Technicians must consult manufacturer specifications and verify compliance. Published tolerances serve as guidelines, but real-world alignment decisions often require engineering judgment. Dynamic movement, determining the alignment state. Dynamic movement refers to shaft positional changes between idle and running conditions. Causes include thermal growth, pipe strain, structural deflection, and operating load variation. This slide explains the need for thermal growth compensation during alignment and why as-found cold alignment may not represent operational alignment. Engineers must assess dynamic movement to align machines for true running conditions. Technicians determine whether machines exhibit offset, angular, or combined misalignment by analyzing measurement data. This slide explains how alignment state is diagnosed using dial indicators, laser alignment systems, or basic tools such as straightedges and feeler gauges. Understanding the alignment state is crucial before applying corrections. Using a straightedge or feeler gauge, checking and correcting soft foot, using dial indicators. Straightedges and feeler gauges offer a basic method to identify gross misalignment. While not precise enough for high-speed machinery, they provide quick initial assessments. This slide describes proper contact techniques, limitations due to coupling runout or surface irregularities, and the situations where these methods remain practical. Soft foot occurs when a machine foot does not sit evenly on its base, causing distortion when bolts are tightened. This slide explains methods for checking soft foot, such as single bolt loosening tests and dial indicator measurement under each foot. Corrective actions include adding or removing shims, cleaning foot-to-base contact surfaces, and correcting bent feet or base irregularities. Dial indicators provide precise measurement of shaft movement during rotation. This slide discusses setup requirements, indicator mounting, runout effects, bar sag correction, and interpretation of indicator readings. Dial indicators remain widely used, especially where laser tools are unavailable. Dial indicator limitations, the rim and face method. Dial indicators require careful mounting and are sensitive to setup errors such as sag, thermal drift, and bracket flex. This slide explains these limitations and how they affect reading accuracy. It also clarifies why laser alignment systems have largely replaced dial-based methods in precision applications. The rim and face method measures angular and offset misalignment using readings taken at the coupling rim and face. This slide describes setup geometry, calculation methods, and typical sources of error. While effective, the method requires high technician skill and careful mathematical interpretation. The reverse dial method, laser alignment systems. The reverse dial method measures alignment using two indicators mounted 180 degrees apart on the shafts. This slide explains the method's geometry, how to calculate corrections, and why it improves accuracy over the rim and face method. The method remains useful where laser systems are unavailable. Laser alignment systems provide real-time, high-precision measurements with simplified setup and automated correction calculations. This slide covers system components, lasers, detectors, brackets, and benefits such as sag-free measurement, digital guidance, and documentation capability. Laser tools reduce human error and ensure repeatability. Moving the machine, vertical, shimming, moving the machine, laterally. Vertical corrections involve adding or removing shims beneath machine feet. This slide explains calculation of shim changes based on angular and vertical offset misalignment values. It emphasizes maintaining shim cleanliness, avoiding stacked thin shims, and rechecking for soft foot after adjustments. Lateral movement corrects horizontal misalignment. This slide describes using jacking bolts, controlled tapping, or motor slides to adjust machine position. It also explains the importance of loosening and tightening bolts in the proper sequence to maintain control and prevent movement errors. Conclusion, key points, final slide. The conclusion summarizes that proper shaft alignment significantly improves machine reliability, energy efficiency, and component lifespan. Advanced methods and high-precision tools have made alignment more accurate and repeatable, but technician skill and mechanical preparation remain equally important. The slide reinforces alignment as a multi-step engineering process that relies on accurate measurement, understanding of machine behavior, and disciplined correction techniques. This slide consolidates major takeaways. Alignment must consider dynamic movement and thermal growth, tolerance selection must match machine speed and application, soft foot must be corrected before any alignment measurement, choosing the correct measurement method improves accuracy, and precision corrections such as shimming and lateral movement require proper technique. Emphasis is placed on the relationship between alignment quality and long-term machine health. The final slide closes the presentation and may include thanks, contact information, or further resources. It marks the end of the alignment training session and reinforces that attendees can request additional modules including misalignment vibration signatures, thermal growth modeling, or advanced laser alignment workflows.